Hello everyone, welcome to the Makers Meetup. My name is Rabab Hassan and I am the co-founder and CEO of Karakeeb Makerspace, one of the first makerspaces in Alexandria, Egypt. Today, the discussion will focus on how makerspaces enable innovation, fabrication, and prototyping from concept to execution. As you know, makerspaces are more than just workshops. They are hubs of creativity where people from all backgrounds come together to build, learn, and innovate. This session, we will explore the world of makerspaces, the role in fostering innovation, and the tools and technologies that make prototyping possible. During our session, we will know what is a makerspace, fabrication and prototyping techniques, tools and technologies you will find in most of the makerspaces, prototyping workflow from ideation to testing and iteration. Also, success stories in different makerspaces around the world, and what is the next step for you as a maker in the maker community. Let's start. Who are we? Who is Karakeeb Makerspace? Karakeeb Makerspace was founded in 2013 with a mission of spreading the making culture among people, especially those from non-engineering backgrounds. Initially, the focus was on university students, but the impact of the programs led to a broader expansion. Today, Karakeeb Makerspace serves people from all walks of life, ranging from young children to seniors, empowering them with hands-on skills in technology and innovation. The goal is simple: democratizing access to knowledge and tools so that anyone, regardless of expertise, can bring their ideas to life. Before diving deeper, it's important to clarify what exactly is a makerspace. A makerspace is a collaborative workspace designed to facilitate hands-on learning, creativity, and prototyping. These spaces provide access to a variety of tools, from high-tech equipment like 3D printers and CNC machines to basic hand tools and sewing machines. The key idea behind the makerspaces is inclusivity. They are open to students, entrepreneurs, hobbyists, and professionals. And you may ask, why are these spaces essential? They are essential for encouraging creativity and innovation, providing access to expansion fabrication tools, fostering collaboration among different disciplines. Makerspaces remove the barriers between an idea and its execution, making them critical in today's fast-paced innovation landscapes. Makerspaces offer a hands-on learning environment, which is often missing in traditional education. The ability to learn by doing allows individuals to experiment, fail, and iterate. And that's an essential part of the innovation process. Let's talk about some key benefits of makerspaces. You have an access to high-tech tools. Many fabrication tools are too expensive for individuals, but makerspaces provide shared access. You will find the support for prototyping, whether it's 3D printing or concept or using a CNC machine for precision cutting. Makerspaces enable rapid prototyping. Collaboration and problem solving. People from diverse backgrounds work together to create solutions for real-world problems. Makerspaces bridge the gap between learning and doing. A deeper look into the technologies that make this possible is necessary. Before we talk about another technologies and prototyping, let's define what is a digital fabrication. What is digital fabrication? Digital fabrication is the process of creating physical objects using computer-controlled machines. This enables precise and efficient production of prototypes and products. Digital fabrication is that it allows for rapid iteration and customization, making it ideal for both prototyping and small-scale production. You will find some common digital fabrication techniques include 3D printing, CNC machining, laser cutting, We have a detailed breakdown of those techniques follows. Let's talk about 3D printing. 3D printing is an additive manufacturing technique that creates objects by adding material layer by layer. It's widely used for prototyping custom parts and even end-use products. We have different technologies related to 3D printing. We have FDM, SLA, SLS. FDM uses thermoplastic filaments like PLA, ABS, and PETG. SLA utilizes liquid resin cured by ultraviolet light and that ideal for high detailed print. We have also SLS and that works with powdered materials like nylon and may be used in industrial application. We have also another technique called CNC machining. CNC stands for computer numerical control. This is a subtractive manufacturing process that cuts material from a solid block using a computer control tools. We have different types of CNC machining. We have CNC milling, CNC turning, CNC routing. Also, one of the famous technique is called laser cutting and engraving. Laser cutting is a precise method for cutting and engraving a variety of materials using a focused laser beam. We have different types: CO2 laser cutters, fiber laser cutters, diode laser cutters. Also, we have different techniques like injection molding. Injection molding involves injecting molten material into a mold cavity, allowing mass production of consistent plastic parts. We have different types of injection modeling like thermoplastic injection modeling, liquid silicone rubber modeling. Also, we have PCB fabrication, printed circuit board. PCB fabrication involves designing and manufacturing electronic circuits that power various devices. We have 3 different techniques: etching process, CNC PCB milling, SMD stand for surface mount device assembly. Each of these methods plays a critical role in turning concepts into tangible products. Let's take a deeper understanding of the tools that make these techniques possible. Makerspaces are equipped with a variety of tools and technologies that enable users to design, prototype, and create functional projects. These spaces bridge the gap between ideation and execution, offering access to equipment that might otherwise be too expensive or complex for individuals to own. And now we're going to explore the key tools and technologies commonly found in makerspaces and their application. As we have the 3D printing technique, we have 3D printers used for rapid prototyping and manufacturing. We have also laser cutters, CNC machines, computer-controlled milling and cutting machines that shape material like wood, metal, and plastic. The most famous and common station in most of the makerspaces is electronic and microcontrollers, like having Arduino, ESP32, Raspberry Pi, Swazidev, most of them used for IoT, robotics, and automation projects. Also, soldering station and circuit assembly tools, and those essential for working with electronics components and PCB fabrication. Vinyl cutters and screen printing equipment used for branding, custom merchandise, and textile designs. You will find hand tools and power tools like drills, saws, welding equipments, sanding machines, used for general construction, mechanical assembly, and hands-on prototyping. Most of makerspaces have advanced technology like bioprinting, biomaterial, AI and machine learning integration. It depends on the makerspace itself. One of the main factors of the successful prototypes is choosing the right machine for your prototype. Selecting the correct machine for a prototype is essential for efficiency, cost effectiveness, and achieving the desired level of precision. The choice depends on factors such as material type, design complexity, and production scale. We have different factors considered when choosing a machine. One of these factors is material compatibility. Some machines work best with plastic, while others are ideal for metal or wood. Also, precision requirements. High detail projects may require SLA 3D printing or fiber laser cutting. Also, the production volume. Single prototypes can be printed using 3D printers, but large batches may benefit from CNC machining or injection molding. And also speed versus cost. 3D printing is cost-effective for one-offs, whereas CNC machining is better for repeated precision cuts. When you select a machine, you should think about a prototype need. What the needs of your prototype? For concept models, use FDM 3D printing, quick and cost-effective. For high precision parts, use SLA 3D printing, smooth, detailed surfaces. For structural strengths, use CNC milling or routing, ideal for metal and woods. And for customized cutting and engraving, use laser cutters, perfect for intricate designs. And for electronic prototyping, use PCB fabrication tools. Choosing the right tool enhances efficiency and ensures that the final prototypes align with design's specification. And now let's move to the prototyping workflow. Prototyping is a structured process of transforming an initial idea into a functional product. It's an essential workflow in innovation, ensuring the concept evolved into well-tested, viable solutions. The process is divided into 5 critical stages: ideation, digital design, material selection, fabrication, testing, and iteration. Each step is essential in transforming concepts into real-world solutions. The first stage is ideation. Ideation is a brainstorming phase where raw ideas are explored, challenged, and refined. This stage encourages creativity and problem solving through various techniques. We have different techniques: mind mapping, sketching, design thinking. When you use mind mapping, visually organizing ideas and their connections, while sketching, it's a hand drawing rough designs to explore form and function. But in design thinking, a user-centric approach focusing on solving real problems. Let's take an example to make it clear. A startup wants to create a smart irrigation system. They began by identifying user needs, farmers requiring an affordable, automated way to manage water efficiently. After detecting the problem and coming up with idea, we move to the next phase: digital design. Once an idea is selected, it must be digitally visualized. This involves using computer-aided design. To create 3D models or electronic schematics, we use one of the most famous softwares, Fusion 360, and ideal for mechanical and product design. Also, SolidWorks, it's a professional tool for detailed industrial designs. Also, we have a Tinkercad, that's a beginner-friendly platform for simple prototypes. Applying on the same example, the smart irrigation system is designed in Fusion 360, where the casing, water flow mechanism, and electronic components are modeled for visualizing and testing. After making the digital design, we need to choose the right resource in material selection phase. Selecting the correct material is essential for a functional prototype. We have different factors in this phase: durability, weight and flexibility, environmental consideration. In durability, you should ask yourself, is the prototype meant for long-term use or short-term testing? While in weight and flexibility, you should think, should it be lightweight, PLA plastic, or rigid aluminum? And environmental consideration. Does it need to be water resistant or biodegradable? To make it clear, applying on the same example, the smart irrigation system casing is chosen to be PLA for initial 3D printing tests, with a plan to use waterproof EPS plastic for the final version. And after choosing your right material, it's the funny phase, fabrication, bringing it to life. At this stage, the physical prototype is created using the appropriate fabrication techniques: 3D printing, CNC machining, laser cutting, PCB manufacturing. Choosing the right technique, it depends on the prototype itself. Applying on the same example, the first prototype of the smart irrigation system is 3D printed, while its electronic components are assembled on a custom designed PCB. It depends on the application. After fabricating your prototype, the very important phase coming up, testing and iteration. Rarely does a prototype succeed on the first attempt. Testing identifies flaws and iteration ensures improvement. We have different stages of testing: functional testing, durability testing, user feedback. In functional testing, we ensure all components work correctly. But in durability testing, we evaluate strength, flexibility, and environmental resistance. A very important stage is a user feedback. Gather insights from real users to refine usability. Applying on the same example, farmers test a smart irrigation system. Some find the interface difficult, leading to design refinements for a more user-friendly control panel. After finishing the fifth phase, testing and iteration, we moved from the 5 phases of workflow prototype. So let's talk about some success stories around the world of products that made inside Makerspaces. Makerspaces have transformed the people. Makerspaces have transformed the way people approach problem solving, providing access to tools and technologies that help address real-world challenges. Here are some powerful examples demonstrating the role of makerspaces and digital fabrication in making a difference. One of them, 3D printed prosthetics, affordable solution for healthcare. Traditional prosthetics are expensive and inaccessible, particularly for children who outgrow them quickly. Makerspaces developed a prosthetic design using 3D printing, make it affordable, customizable, and easy to have an access of it at any age. And that have an impact. Thousands of children worldwide now have access to prosthetic lamps that can be adapted as they grow. We have also IoT-based smart farming, reducing water waste in agriculture. Farmers struggle with insufficient irrigation, leading to excessive water usage and environmental damage. So Makerspaces developed IoT-powered irrigation system where using soil moisture sensor and automation to optimize water distribution. So farmers have reduced water waste by up to 50%, improving sustainability and food production efficiency. Another success story in one of the makerspaces is open source assistive technology, making daily life more accessible. Assistive devices for individuals with disability are often costly and unavailable in developing regions. Makerspaces have developed open source designs for smart wheelchair, voice-controlled appliances, and braille printers using affordable digital fabrication techniques. Another success story in one of the makerspaces is recycled plastic filament, transforming waste into usable material. Plastic waste is growing environmental crisis. Makerspaces like Precious Plastic have developed the machines that recycle plastic waste into 3D printing filament, promoting sustainability. This initiative helps reduce landfill waste while encouraging circular economy in digital fabrication. Some of the local success stories in different makerspaces, especially in our makerspace, is Eco Khadra. Eco Khadra, a smart trash bin for sustainable waste management. People often struggle with waste segregation, leading to poor recycling rates. Eco Khadra, a smart trash bin, was designed to promote waste sorting using built-in cameras, interactive feedback, and social engagement, and that encourage responsible waste disposal through gamification, reducing environmental impact in urban settings. Also, Animation Station, improving stop-motion animation production. Also, Retro Station, bringing arcade nostalgia to modern audiences. These success stories demonstrate the power of makerspaces in fostering innovation, solving social and environmental challenges, and making technology more accessible to individuals and communities around the world. Makerspaces are not just about tools, they are about people, innovation, and collaboration. Whether you are an engineer, an artist, or an entrepreneur, this is a place for you in the maker community. I encourage you to explore a makerspace, start experimenting with digital fabrication, and keep innovating. Thank you for joining this session, and I look forward to seeing what you create.